In the last video, we talked about failure. Good systems don't avoid failure. They decide where it happens. If you haven't seen that video, I would start there, because what we're about to cover builds directly on it. But even if you haven't, there's a second question every system has to answer, not where it fails, but what happens next. Because once something starts to fail, something else decides how far that failure goes. Does the system slow down? Does it isolate the problem? Does it keep accepting work? Or does it push back? That is the role of control, not as a feature, but as a structural part of the architecture. Every system operates within limits: capacity, latency, dependency constraints, and under normal conditions, those limits are invisible. But as pressure builds, the system begins to reveal how it actually behaves. Requests don't just flow through the system, they interact with it. They compete for resources. Failures trigger retries. Retries create more load. Load accumulates in queues, and unless something intervenes, that interaction doesn't stabilize, it amplifies. So the question is not whether your system has control. It does. The question is how that control is expressed. Because control is not a single mechanism. It's a set of structural decisions about how the system responds when it should do less. These are not separate techniques. They are different ways of applying control. Rate limiting defines how much demand is allowed in. Circuit breakers define when the system stops, depending on something unstable. Backpressure defines how upstream behavior is influenced by downstream conditions. Bulkheads define how much failure can be contained within a boundary. Retries define whether recovery is attempted and how far that attempt is allowed to go. Each of these introduces a constraint, and those constraints shape behavior over time. This is what turns a system from something that reacts into something that regulates itself. Because without control, the system has no way to say no. It keeps accepting work. It keeps retrying. It keeps distributing load. Until those control decisions begin to conflict with each other, and when that happens, failure doesn't stay where it started. It spreads. Not because the system is poorly implemented, but because it was never designed to limit itself. This is where control connects back to failure. Failure determines where the system is allowed to break. Control determines how far that break is allowed to move. If failure is unstructured, the system breaks unpredictably. If control is missing, it doesn't stop breaking. So when you design with a control pattern, the focus shifts from handling requests to shaping system behavior. You start asking different questions. Where should the system push back? When should it slow down? What should it protect first? What should it let go? Those decisions don't sit in one place. They are expressed across the system, at the edge, between services, inside execution paths. And together, they define the conditions under which the system remains stable. Because stability is not something you add, it is something the system maintains through control. And once that becomes visible, patterns like rate limiting, retries, circuit breakers, and bulkheads stop being implementation details. They become part of the same architectural idea, the system deciding how much it is willing to do.